Hello and welcome back to WA Real. I'm your host Bryn Edwards. WA Real brings you real and authentic stories from fascinating people here in Western Australia. Stories to inspire and guide you to take action to be all you can be. Today we're going to consider and explore life on an atomic level with physicist Professor Igor Bray. Originally born in Leningrad, USSR, Igor moved to Adelaide in 1972 at the age of 11. He then moved to Perth in 2001. Graduating from the University of Adelaide with a PhD entitled Gravitational Lens Effects of Galaxies and Black Holes, Igor has held numerous positions before becoming head of Curtin's Department of Physics and Astronomy in 2010. He ranks in the top few in the world in the field of atomic and molecular collision physics and is responsible for several major paradigm-shifting research breakthroughs during his career. In 2017, after publishing more than 450 academic papers and presiding over research that attracted over 10 million in funding for Curtin University, Igor was recognised by his peers with an election to the Australian Academy of Science. Igor, welcome to the show.
Thank you so much for that wonderful introduction.
Indeed. So, one of the things I like to start with in my conversations is understand how people found their way to Western Australia. Mm-hmm. But before we start with Western Australia, obviously you were originally born in the USSR, Russia.
Yes. Yeah.
How did you find your way from there to Australia, particularly in 1972?
Yeah, indeed. It's unfortunately somewhat of a traumatic story, and my father and mother were divorced. Not that I knew it, because we still lived in the single flat that had just now 2 rooms, and I wasn't aware of any of the issues. But the next thing I know is that my mother married an Australian, a musician. So my mother was teaching English at a Russian university, well, in Leningrad. Now it's called St. Petersburg. And so whenever there were Westerners and coming through, she was part of the Russian English Friendship Society, and she would take them around then Leningrad to show them the beautiful buildings, and that's how they met. So he was a musician, his name is Igor Bray, and he was the principal clarinet player of the Adelaide Symphony Orchestra. Anyway, they met, they fell in love, decided to get married. And I was oblivious to all this, and but the next thing I know is that we're heading for Australia. I was utterly stunned. And and later, of course, a lot of things had to happen in the background. And while this was a fantastic outcome for me, it was a rather tragic outcome for members of my family in the background, which I only found out about at a later stage. But not dwelling on that sort of past, so I came to Adelaide in 1972, as you said, and I had to learn English. And it was, I really found what it's like to go from being a really popular kid to whom words come very easily to complete stranger and absolutely unable to communicate with my peers or anybody apart from my mother. And it was a very sort of traumatic and difficult period. But as with most things, what doesn't kill you is good for you. So for my personality, it's probably just what I needed, because I got to see how difficult life can be for those who are not so fortunate. So I was still good at maths and science, and I studied that at school, and I heard there was a course called mathematical physics at the age of 15, and I knew it was for me. And so that's how I got into sort of mathematics and physics, and at every stage doors kept on opening for me.
Right.
And so from having come to Australia, it was like coming to a paradise, and just where, more than that, it's just there were always people there who somehow looked after your interests and supported you all the way through. And I can give you a long story, but eventually I ended up with a PhD, as you described, in a very different area to where I work now, and that's a really interesting story as to how I ended up in other areas. But eventually I got married. I married a girl, Anne, from Adelaide, and we had 2 children, and through work we ended up finding ourselves in Perth in 2001. And it's a most wonderful place to live, to raise a family, and to do fantastic stuff with wonderful people around me.
You see yourself staying here for some time?
Oh yes, yeah. So it was interesting when we came, which is something that really surprised us. People asked us in Western Australia, "How long are you coming for?" And this was a rather unique and sort of environment. People somehow didn't expect you to stay. And Anne had a beautiful response, and she said, "We've come here for good."
Right.
And it turns out it was literally true, as well as symbolically true. Is that we've raised our children here. I mean, there were 4 and 6 when we came, but they certainly feel part of Western Australia. And I tell all of the students that Perth is the most beautiful, wonderful place to raise a family, but it is your base to be successful on the world stage.
That's interesting.
Yeah.
Why is that?
Well, first of all, for those people who have travelled the world, they will readily understand what I mean by saying that Perth is the most wonderful place to raise a family. Other people will take it a bit for granted. But our isolation, that historically was problematic with the internet, the age of the internet, it is far more advantageous than problematic, because you can take the time to get things done. And I'm not overwhelmed like my colleagues in Europe or United States. They've got so many conferences and meetings, and these are wonderful, exciting things, but you don't get things done whilst you're busy travelling and talking. You just have to find that right balance. And because people understand if I say no to an invitation to go to somewhere, because I've been travelling. I don't want to travel, to Europe or United States, at most more than 3 times a year. Roughly twice is about optimal for us. So, and that means I have to be here, making sure the department runs well, and I have most wonderful people to work with, and I couldn't do my job without them. But you have to pay attention and address problems when they arise, and if you're absent, you can't do that. And I love my research, I love working with my students, and you have to be here to do that. So to be a scientist, Perth is an ideal place.
Right. I like that.
Yeah.
Just going back, how long did it take you to actually feel comfortable with English, having moved here?
Well, I guess one of the things I'm fairly proud of, so I came at the age of 11, which was halfway through grade 6.
Yeah.
By the end of grade 7, I had an A in English. However, that A was a more of an academic A, not a conversational A.
Right.
And so for a long time, as any immigrant would know, it is impossible to understand the spoken English on television or in films, because it's just too quick. And I would say that conversationally, I felt more comfortable after about 2 years, but in written form, to write things, it's a lifelong activity. I make the case that communication is the most important skill for any human being in any field, but it is a lifelong development, and I have to write well. So the logic is fairly clear, but I'll still get the A's and the Th's sometimes in the wrong place, because I'm just not a native English speaker. And that will always be a little hurdle for me, but it has not been, so it would have been sort of debilitating through high school years. I remember not understanding questions in mathematics because of the language.
Right.
And I developed a skill to say, well, I understand the context in which this question is being phrased. I wonder if what would be an interesting mathematical question to ask in this context, and I would answer what I think the question might be.
Right.
And sometimes I would be answering the right question. Sometimes the teacher would say, but that's not what I asked. I said, I'm sorry, I couldn't make it out.
A perfect answer to a different question.
Exactly, yeah. So, those things I remember very clearly.
Yeah. And do you still speak Russian now? Or?
And not very well. It's language, if you imagine how you would speak at the age of 11 English, but then not have any practice for 30, 40 years. Then you can understand you will have forgotten some, and it's language of a child. So there's no sophistication to it. But I have been back to St. Petersburg, Moscow, parts of Ukraine. So I still have family there. And after several days, I can get back into conversational Russian. No chance of reading or writing. Well, reading is not so bad, but writing, no chance.
Yeah. So that must leave you in an interesting place then, having started life speaking one language and then moving to another, and neither of them ever really bedding in and seeing them through your informative years of childhood.
Yes, I remember a particular moment in my life when I was forgetting Russian and had very poor knowledge of English. I said to myself, I have no language. It's very confronting. I could not express myself in any language. It wasn't sophisticated enough in English, and I had English speakers around me, and I didn't have the Russian development to express any sophistication either. So that was a very confronting time. It didn't last that long, of course, but nevertheless, the lesson learned was invaluable. Humility really teaches you a real understanding for those who are in a similar position, and around the world around us there's many people in that situation. And I was lucky, I was 11. What about a middle-aged or later person changing languages or being in a different country? It must be much more difficult.
So what was it about maths and physics that drew you in?
I think I'm wired that way, in all honesty.
Right.
I always loved it. So it's not simply I'm good at it. I love it. I get excited. My teachers from school will remember me exclaiming in the middle of their derivation when I would see where they're going. And I'd say, oh, that's brilliant. And so, well, I haven't finished yet, right? It's me. And I have learned that then I'm not the only one, of course, who has this real love and passion for the mathematics. I am wired that way in both rational side and emotional side.
Right.
I just enjoy it so much. And it's somewhat similar to sport and music. I love my sport. I love my music, right? I am really wired well for maths and science. I'm not as well wired for music as my wife, who has almost perfect pitch as a violinist, or my musical family. My mother was a musician as well as a teacher of English, and her mother and grandfather were musicians. But I gathered that they must have learned early on that I didn't have the musical ear that was commensurate with what was expected in the family. So I was encouraged to go out and play soccer. So, one of my greatest achievements is to play for South Australia against Victoria, centre forward for state high schools.
Excellent.
In 1978. But I've always really loved most things that I did, and I encourage my students now to have this balance of life between. Many of them are wired to be very, very good at maths and physics. But I assure them that their maths and physics will do so much better for the sport they play and the music that they engage with as well, to form a more complete approach to life.
Yes. Yes. So, just give us a potted history of how you then went from school to university to PhD to...
Yeah, okay. So the high school that I went to is Unley High, and funnily enough, Julia Gillard, our ex-Prime Minister, was in the same class.
Oh, right.
Right, and as was my wife, but though Anne and I went out together at the university. But the love for the maths and the physics, and a lot of it was nurtured by my teachers at Unley High. I'm forever grateful to them, and they were the ones who made me aware of mathematical physics being available at the University of Adelaide. So at the age of 15, I knew this was for me. So I went to Adelaide Uni and I studied mathematics, computer science, physics. I did a bit of logic and philosophy, also wonderfully useful subjects to complement the other more technical subjects. And I found it quite challenging at the beginning, because at school I had never learned to study. I had learned to play soccer. I was quite good at that, but I didn't know that you actually had to study before you turned up for an exam. It just, things came fairly natural to me. Right. Well, that didn't work at university. I discovered that I would do half the paper in the time available. I'd get almost 100%, but then there was half the exam paper that wasn't done.
Yeah.
So I'd get relatively low marks at the beginning of my studies, and then I realised, well, what do other people do? And apparently people studied before exams and through the semester. So I developed a good work ethic, learning from my peers who were doing much better, and then my grades came up to distinctions as well. And I studied mathematical physics. I did my PhD in that area because I loved it. And then, well, sort of the world opened up. And I keep saying also to my students that in life you have to be opportunistic. You never know what interesting opportunity will arise. But if you're good at things, something definitely will. And the big challenge is to deal with the options that are made available for you. And because it's destabilizing. You think you have a path, and then something out of left field comes up and says, oh, here's an opportunity. And in fact, my job now is to create, I say to the students that my job is to unlock as many doors for you as I possibly can. Your job is to choose which one you want to walk through.
Yes.
Right? And so now I engage with industry companies. They say they want to have access to our students. We have brilliant, fantastic students. And industry is very, very fortunate to get access to them. Some will want to go in more academic areas of physics. Some will want to go into industry. Some will go to government areas. So all of these things, all of these opportunities will arise. And this is what happened to me. I was doing one thing, suddenly another opportunity came along to go to a different university. We're still in Adelaide, but they were looking for somebody to be a research assistant. I only found out about this opportunity through a friend. I investigated it. I got the job. I was doing that. I already had an opportunity to go to Tucson, Arizona through a postdoc, because of the people behind, without my asking, people organized jobs for me in the United States. I even got a phone call from the United States saying that the offer is in the mail. I was warned that my wife is an alien, so she's formally not allowed to work, but they will probably find something for her. Well, it's a bit offensive for me, calling my wife an alien.
I was going to say that. Yeah.
So this is not a way to get into my good books.
Yeah.
So Anne is my best friend. She was the best friend when we got married. She's my best friend at 35 years later. So I said, well, okay, we organised for someone to stay in our house, but 1 week passes, 2 weeks passes, nothing happens. Out of the blue, another offer comes over from the local university to change fields and be a postdoc. This is something you do after a PhD. For 5 years, they had resources to change field to this quantum collision theory. I came home and I said, sweetheart, you wouldn't believe it. I've just been offered a 5-year position to stay in Adelaide. And for a number of personal reasons, we hadn't notified our family as yet, and I had a younger brother who sort of needed me a lot. And I did some investigation. Well, who are these people? How good are they? And I found that they're one of the strongest groups in physics in all of Australia at the time. A nice balance of theory and experiment all in one place. So I decided to accept the offer, because the one from the United States, not that I had seen it, but I knew that it was like typical US, 9 months of the year, and then the 3 months you have to find your salary elsewhere, and then potentially extension.
Have your wife called an alien?
Yes, and but what turned out, the reason it had not arrived on time is because the secretary in the United States did not know how to spell the word Australia. The offer was sent to Australia, not Austria, but to Australia. And so eventually, a month after the phone call, the offer did arrive, and we could see that it went to Europe first, bounced around there for a while before they worked out it wasn't Austria, it was actually Australia. So, one can make the case that if the offer had arrived typically a week later after it was sent, then I may have said to everybody that we're off to the United States, being oblivious to the potential of being able to remain in Australia. And because this group were a world-leading group in Australia, I realised that I wasn't going to be disadvantaged by staying in Australia working in this area of quantum collision theory.
Yes.
This was at Flinders University, and this decision we made around 1985, 86. And so that's what changed me to that field. And from then on, I've had research-only appointments. So I've always had a funding from the Australian Research Council,
right,
to have for my own salary. So not just as a grant to work with,
do a project,
but actually for my own salary. And that worked wonderfully well for me until about the year 2000. And then 1 year, I was not successful with a particular grant for further salary. And I was a bit upset about that because that was essentially a catalyst for a midlife crisis, if you like.
Right.
So what am I doing with myself? What is my life? Where's it going? At that time, I have 2 children, and so and I talked, but very quickly, as other people found out that I was not successful on this occasion, I had opportunities to go to Melbourne or to ANU in Canberra, and my colleague in Perth quickly created a professorship position for me. At that moment was at Murdoch University, and but they asked that I reapply, and for this, because it's very convenient for universities if the salaries of their staff are being paid by the Australian Research Council,
yes,
rather than themselves, of course. And
right.
Turned out, so we came to Perth. Basically the last few days of August of 2001, and within 3 months of my arrival, the second time I made this application, I had over $1 million in research funding, but this time I didn't go to Adelaide and went to Murdoch University at the time, and we never looked back since. Still looking at
collision theory?
Yes, still looking at quantum collision theory, and this is something that we're still working on, and it's very, very, it matches my personality because it is about doing things that are really useful and practical for society. I'm a person whose culture is that if the taxpayer is funding this wonderful lifestyle, I must give back to the society. It is a delight. It is my pleasure. That's why I go to a lot of schools. I do a lot of outreach activities, and I tell them about how we turn the science that we're doing to practical outcomes for the benefit of all.
Cool. So, tell us a bit about. This is a very open leading question.
Yeah.
Tell us a bit about quantum physics.
Yeah.
I first encountered it when I watched the film What the Bleep Do We Know?
Right.
Since then, I've always had a bit of an interest in it, and to be completely transparent, I have an A level in maths and physics myself from back in England, coupled with an A level in Latin. So
right.
There you go. Nice and logical, all three. The bit I find particularly fascinating was this original. It was originally presented as the double slit.
Yeah.
Where the electrons are passed through
Yes.
the two slits,
Right.
and out the back, instead of you probably described this much better than I, but where scientists were expecting electrons to pass through these small little slits, these gates, and pop out at the back, like they would expect tennis balls thrown through.
Correct.
You see a line at the back. They found multiple lines across the back.
Correct. Yes.
And therefore, these electrons were moving in a wave format.
Yes. Yes.
And then when they then attempted to observe what was going on, the electrons then acted like particles and went through. And so there's this whole thing about when we are not looking at electrons, which are the nucleus of atoms, which is what we're all and everything is made of. They act like waves full of potential. And then when we look at them, they turn into something solid and material.
Yeah.
Is that correct?
Oh, yes, yes. So those were indeed wonderful experiments, and at once difficult to understand using terminology that comes from everyday experience. But for scientists, once they get used to working at that quantum level, that delightful and very interesting aspect of these particles, such as photons behaving like either a wave or a particle, and even electrons behaving like a wave or particles, that is something that we are comfortable enough with. However, there are aspects of quantum mechanics that have no explanation and may be a little bit difficult to get them across. But these ideas, such as superpositions of particles both being in more than one state at once, are the reasons that we are going to hopefully have quantum computing coming along. And some of the issues of entanglement that somehow, I use the term correlated randomness. And we have no universally acceptable explanation for these phenomena that can be measured. And
so for the everyday person who's listening to this, give us a brief introduction to what entanglement and superposition.
Okay, so the idea, so people are familiar with the ordinary computer, and that you have either a 0 or a 1. Okay, well, with a computer with superposition, a state can be in a combination of 0 or 1. So there's somehow more information is possible rather than these two extremes, right? And you can take advantage of that. You can create special algorithms that can take advantage of that, and using those algorithms you can decode cryptography. All of those things can open up. You can decode large prime numbers into its factors. So there are special techniques that can take advantage of this idea of superposition. It doesn't make much sense. And the act of observing, it's an interesting point, forces it into either 0 or 1. But if you don't make that observation, then you can work with the fact that there's in a superposition of both those states.
So we're actually going to make computers that,
yes,
in effect,
yeah.
that.
So the Australian of the Year is Professor Michelle Simmons for 2018, and she's a quantum mechanic like myself, and she is and her group are building a silicon-based. They put phosphorus atoms inside silicon-based media to try and create these qubits and take advantage of quantum, what I call qubits, not ordinary bits 0 or 1, but they call them qubits for quantum bits, to try and take it and create a supercomputer based on that idea. But again, that part is also not so bad. The really awkward part is this idea of entanglement.
So what is entanglement?
So entanglement, so let me perform the thought experiment. Let's see if that comes across in audio. So if you start off with, say, something like a helium atom. Helium atom is a very inert atom, has 2 electrons going around and round. And those electrons are entangled in the sense that the total spin of those states must be 0, because by Pauli principle, Pauli exclusion principle, that's the only possible way those 2 electrons, one spin has to have spin up and the other one must have spin down, so the total spin is 0.
That's why they're going around the outside.
They're going around and is bound to, very tightly bound.
Minding their own business as a helium
Exactly,
atom.
right? You come in with a photon, and it's sufficiently energetic that both electrons go out. So you have double ionization. It's called double photoionization. And you can measure the spin of either electron. And if you were to measure the spin of one of those electrons, it will be completely random, up, down, up, down, up, down. You cannot in any way predict what that measurement will be. You can also measure the spin of the other electron. It'll be up, down, up, down, up, down. You have no idea what it will be. And but you can also do that in coincidence. So you measure them together. Now when you do something in coincidence, you can say that even the speed of light, so that of course cannot reach from one to the other because you do it at the same time.
Yes.
Okay? If something's at the same
speed
time,
of light moves.
Yeah, because it's at the same time, or in practice within a small delta, right? But if they do it far enough apart, then even light cannot travel from one side to the other in the time to make the measurement.
Yeah.
But if you've measured one to be up, the other one will be down. So you can say, well, if each one is random, how come you have this correlation?
And it's a fixed correlation.
And it's a fixed, and it doesn't matter how far apart. So these electrons remain entangled so long as nothing else interferes with them.
Yes.
Until that measurement. And no one can really have a good explanation for this. So in quantum mechanics, we often say that no self-respecting quantum mechanic, and I'm one, will say they understand quantum mechanics.
Right.
And we also follow it up with that if you don't understand what you're doing, don't worry, just calculate.
Just calculate.
Right? So we know how to do the calculations. We know how to get things right in terms of comparison between calculations and experiment.
But
we don't understand
why,
how that is possible.
So let me get this straight. You can have these 2 electrons that you've split, and they were originally had this relationship around a helium atom. You then split them, and they can be God knows how far apart.
Yes.
And this relationship between when one spins up, the other one will spin down. And if that was to change, then they would both change.
Yeah.
And this happens immediately.
Yeah. The moment you perform the measurement.
The moment you perform the measurement.
When this one, it determines the outcome of this one, you're also determining the outcome of one that is so far away at the time.
So it could be the other end of...
It could be the other end of the universe, if you like.
Yes.
Right? Of course, in practice, we can't do that. But with our modern technology and extraordinary timing, like, people are familiar with atomic clocks that can get things, have an accuracy within a few seconds within the age of the universe.
Yes.
When you can have that kind of timing, we know that we are able to determine the outcome of an object that is superluminally separated.
Yes.
Meaning that even with speed of light couldn't have got there in time to make that outcome.
So that means there is a relationship between them.
There's a constant relationship between them, but the aspect of measuring one of them determines the outcome of the other.
And this is irrespective of time and space.
Yeah.
Which then takes us away. Which then takes us away from the stuff we would have been told at school about time and space being very rigid structures.
Well, it's not so much. Well, I don't know about rigid structures. It's just that it's something we can't get our heads around. We have, we like to relate everything to our everyday experience using our everyday language.
Yes.
But this is a reality of a behavior at that subatomic level that can be measured. Right? This is experimental. No theorist predicted that this will be happening.
Yeah.
Right? It is experimentally observable. And as mathematicians, we have to come up with a theory that does so, and we have. No problem. We can do this mathematically. Well, it's quantum mechanics. But if we want to try and explain, we believe that we cannot, that causality can only happen between events that at least can be connected by speed of light. That's what we believe. We have special and general relativity depend on these fundamental concepts, but not quantum mechanics. In quantum mechanics, it's allowed. So what do we have to say? Well, if you were doing it in gravity, that's not allowed, but if you're doing it in quantum mechanics, it is allowed. Well, it's not very satisfying.
Yeah.
Right? But it's what it is.
So now I can understand why this would be a very exciting place to go and work.
Well, it is exciting in that regard, but in the end, you have to do something that's useful.
Yes.
Right. So we don't take advantage of that entanglement necessarily, but we have to work at that quantum level because the world around us is built from collisions and interactions on that atomic level.
Yes.
Now we're sitting in this room right now, and above us is a fluorescent lamp. Now that's a very efficient way of generating lamp. It's just electron colliding with mercury atoms. And it so happens we have the world's best theory, and we worked with Osram Sylvania, who gave us real US cash to do the calculation, to give them all of the interaction information in order to maximize the efficiency of your standard fluorescent lamp.
Yep.
That's one application. Now we're in the area of even cancer treatment. So there will be something that Australia will be doing for the very first time. It was announced in last year's May budget of building Australia's first what's called proton therapy facility. And the idea is to bombard tumours in the body with protons. And why? Because those protons can deliver their destructive energy just to the tumour without the usual side effects you'll get from standard radiation treatment, which damages healthy cells as well as the cancerous ones.
Yeah. So
our job will be to calculate the stopping power of protons in molecules of biological relevance. And this is very exciting because if you were, any of your listeners to Google proton therapy, they will come across amazing stories of children whose brain cancer has been cured by this process, who otherwise would have undergone kind of therapy or radiation therapy treatment that would leave them blind or deaf, but instead actually cured with no side effects.
It's amazing.
So it's actually extraordinary, and so Australia's coming to this a little bit later than say Japan or Europe or United States, but nevertheless it's coming to Australia as well. So that's another sort of the two rather extremes. We also work in astrophysics with a lot of astronomers, and people can understand that the world around us is made from very small particles, and they are interacting, colliding all the time. So there is no shortage of really interesting application that benefit from a quantitative knowledge of those kind of collisions.
How does things like we were just talking about the entanglement and as you've just rightfully said, our whole everything around us is made from these small collisions, etc., etc., etc. How does that change or shape your view of reality and everything that goes on around us on a personal level?
Yes. So I very much, I don't separate my life into work and non-work.
Yes.
I define myself basically by the people I have around me, my family first and foremost, my friends and colleagues, and the work that I do. It is all connected. You know, nothing is, well, this is work, this is play, this is, you know, I love my sport, I love to play golf. I love the company of golfers who don't take it too seriously, because we joke around and mess around, and it's all good fun. I love music, I love to play, I love to listen. But all of it, it's all of those things together make me who I am. And I say to others that I'm a better scientist for all the music and the sport and my social relationships, and vice versa. Everything supports everything else. So I have a public lecture entitled The Physics of Life, Universe and Everything, with apologies to name escapes me, to Douglas Adams, you know, the wonderful book of Hitchhiker's Guide to the Galaxy. So his answer to the ultimate question of life, universe, and everything was 42.
42, yes.
My answer is physics.
Yes.
Right? And so I do see the world and try to understand human behavior and even organizational structures. I'm saying that everything follows laws of physics. For example, I ask students, where do laws of physics come from? Is it because the physics professor says this is what it is? Well, no. Physics professor has no choice. That plays no role in the matter. Physics laws come from symmetry principles. So, for example, we teach students conservation of momentum. We don't say why. Why is it momentum that's conserved? Why not the square of momentum? You know, or something something else. You know, mass times velocity is momentum. Why that? Why not m squared times v? And the answer is because momentum and space have this interesting reciprocal relationship, that if space is symmetric, where collisions took place, then momentum will have been conserved, and vice versa. If momentum was conserved, therefore space must have been symmetric in that neighborhood. And then you look at humanity. Where do laws of humanity come from? Also from symmetry principles. Do unto others as you will have them unto you. It's just a statement of symmetry.
Yeah.
At the moment, there's a lot of discussion about gender equity. What is that about? Symmetry, male, female? Why have different rules? So the only difference with humanity is that for us it's a choice. It's a cultural choice. For much of humanity we had slavery. Now slavery is not symmetry. Right? The relationship between slave and master is very asymmetric. And in physics we say that if you want to impose asymmetry, you can, but you have to provide a force.
Yes.
And how do you support slavery? Through violence. You provide a mechanism. It's not sustainable, right? You have to keep doing it. Eventually some enlightened person says, maybe it's not nice to treat people that way.
Yes.
I wouldn't like it if it was done to me.
Yes.
Right? It's a statement of symmetry. So I really like, or at least I find it helpful for me, to see the world through the eyes of a person who believes, or whose culture is things happen for a reason, due to understanding the forces in play.
Yes.
That's really important, and makes me find it easy to understand how organizations work. Where do the forces come from? What are the motivations of the individual pieces that make that big puzzle that's called an organization? Yeah. So, I find it very helpful to use the laws of physics and ideas of physics to understand all aspects of the world around me, not just the physical aspects.
Yes. That's fascinating. I like that.
Yeah.
Certainly the symmetry, and like you said, we might put ourselves into a state for a period of time, but if it's not our natural balanced state,
yes,
it requires force. And it's interesting because I had a discussion with podcast discussion with a lady who's a Jungian psychoanalyst, and we talked about the duality of life. And we spend the first 30, 40 years of our lives thinking, I am this, but I'm not that, and I am that, but I am not this, and yet we're both, and yet we like to create this identity for ourselves. And then we came to the conclusion that around about the age of 35, 40 is where people talked about midlife crisis or midlife adjustment. It's very much that I've forced my sense of identity into one area because I might culturally like that. I've been playing with life scripts, etc., etc. But now the force, I can't maintain the force any longer, and now it's time to snap back and consider that I am both things. I am good, I am bad. Sometimes I'm generous, sometimes I'm stingy. Sometimes, I'm a nice bloke, sometimes I'm real grumpy.
Yes.
I am both.
Yes, No, look, it's a point well made. And, for me, that sort of quotes midlife crisis, which it wasn't really, but it's challenging to have to move your family from one city to another. And we had some friends here, very good friends, and so that was fine. But traumatic. It means moving away from your other friends and family. And but it allowed me to reinvent myself. So, for example, because now I had children, I'm a changed person for the fact that we had children. So when I came to WA, it made perfect sense to go to their schools and engage with the teaching profession and be out there, part of the education system, and pay attention to what was happening in the education system. And we had some challenges here in Western Australia that became rather hot political topics, but I was at the forefront there, mostly in a support role for the teachers of the day, but
teachers of physics and
all teachers, in fact,
right,
it turned out. Yeah, it's but a lot of teachers were being forced to do things they didn't believe in. I didn't think that education would be improved by. It was a rather traumatic period. Many teachers resigned, and we lost some of the jewels in the state, but others fought on, and we won. We won that battle, and it took a lot of people, but rather traumatic. But I didn't have to get engaged. But the lives of my children, and that's how we found out about it in the first place. For example, a teacher said that in her class, children were too young to learn to read, which we were somewhat surprised by, because we wondered, how do we support the teacher in her reading strategies? But similar age class next door, that teacher was saying absolutely it's the right time to get children to learn to teach. And we thought, well, part of the so much of the education system is logistics. You can't have those two classes will then go on to the next teacher, and half the class would have learned to start reading, and the others not. How is that possible? So this new other system lost its organizational aspects. They were critically important to efficiency in the education system. So there's lots of story, but the point was, suddenly I found myself engaging in aspects of society that otherwise I wouldn't, because it was the right thing to do. It's that simple.
Yes.
But I chose to. And because I was relatively new, with no history or baggage coming here, I said, this is what I want to do. And that's fine, so I did. That's a bit of an advantage of being able to redefine yourself and go through that midlife crisis and be somebody else in addition. So it wasn't at all a rejection of who I was, far from it. It was an enhancement. I was a more, I would say, responsible member of society, because I was now, together with my wife, raising a family. And of course I project that onto other parents. So I'm there not just for my own children, but I'm there for the children of other parents. And, in fact, the culture that I set in this department at Curtin is that teaching is the most important thing we do, on par with raising our own children. And because many of my staff have young children of their own, they get it.
Yep.
They understand that the primary purpose of a university is to raise the next generation of young people who will go and succeed on the world stage. That's what we are about. But that's not the only thing we do. It's like any parent. We love our children, but we can't be there all of the time just raising our children.
Yeah.
We have to have
your own pursuits,
and you have to bring in resources to the family so that you can feed them and shelter them. All of those things. So as you get older, I think, your sort of activities broaden. And I'm very comfortable with that.
There's also something in there for me, being a parent of an 11-year-old, that when I do get to those golden moments with my daughter where we are exploring growing up, developing, etc., then that and teaching, that at that moment, while she is taking something out of it, I too am taking something out of it and starting to understand things at a much deeper level that I probably took for granted.
Yes, yeah, it's a good point. And I also, it took me a little while to realise that as my children were growing, so was I.
Yes. Because
my relationship with them necessarily needs to change as they get older. A baby is not the same as a toddler, not the same as a young child, not the same as a teenager. Now they're young adults. And yet we've always had a wonderful relationship from the earliest times right through to them now. And then one's 20, one was at 22. And that's... I realised I have to change. I have to grow as they grow. And it took me a little while,
Yes.
to have to let go. Well, they're not 3 years old anymore. They're not 5 years old. They make their own decisions now. And my job now is to support, discuss, not tell, this is what you do or whatever, but engage in genuine conversation and seek, where they're at. What's their world like? Because their world at their age is not the same as my world was when I was their age.
Yes.
Right? And I have to, understand, the social media of today, at that age, when I was that age, there was no social media.
No, there was nothing.
There was no internet, right? So it's a different world, and it's a world that I don't fully comprehend in the same way that they do.
Yes.
Right? So I have to learn.
Indeed.
And they keep me connected.
So there must be parallels between that and your job.
Yes, absolutely.
Yes.
It's all connected. It is all connected. So all of life is about communication, and communication with the younger generation is so delightful. It's so energizing because they have so much energy. The world belongs to them, right? They're about to step into it and take charge, and they're full of enthusiasm, idealism, and I hope that it will never get squashed. And my job is to nurture and to support them, to see and to achieve the best that they can be. It was a lovely line in your introduction.
Yes. Superb. If I could just ask, because it's not every day I get to have a discussion with with a physicist like yourself, and just dive back into the physics a minute. What? It's very being a leading question again, but going back to the Large Collider in Switzerland,
right?
What does that do, and what does it continue to do? Because I remember it being built, and then I remember it not firing because there was certain aspects didn't work.
Yeah, the superconducting magnets weren't working.
Weren't quite working, and yet so there was a whole lot of furore. Then there wasn't, and now I don't hear so much about it.
Yeah. I don't know what stage. So there's many aspects to the Large Hydron Collider. I, in fact, have collaborators there. But what it is known for is for super high energy collisions. So they can create the most energetic collisions here on Earth. Now, these collisions are fairly commonplace out in the universe. But out in the universe, there are no detectors out there to see what are the outcomes of these collisions. Here it's a very controlled environment, and you collide particles together at 0.9999 speed of light. and they break up, and you can see all the constituents. So that's one aspect of what they do, and they found the Higgs boson roughly at the energy where they thought there might be one, but something that was predicted in the 60s, I think, by Peter Higgs, and they led to a Nobel Prize for Professor Higgs, and very exciting time, because there's many aspects. So physics is interesting. We start off trying to explain things on our everyday scale, and to do that we sometimes go down in scale, sometimes go up in scale, try to understand everything.
Chunk up and chunk down.
Yeah. So that's our job, right? Our job is to understand things, and at all scales. But we find that as we get down to very, very small scales, we get a bit stuck. We don't quite understand it.
Yeah.
And we also know that if we go up into higher scales, again, we don't understand what's going on. And that's fine, it's furthest away from our everyday experience, so we shouldn't be too surprised that it's going to take us a while to sort things out, if, and when, who knows. So we build these like Large Hydron Collider as one example of understanding the inner workings of things by colliding them and see what happens when they break up, right? And one of the areas that I'm involved in is another aspect of the Large Hydron Collider is where they can make antiprotons. They can create antimatter. Now, antimatter might sound a little bit exotic, but in fact all of our hospitals have a thing called a PET scanner. PET stands for positron emission tomography. Positrons is a bit of antimatter, an antimatter of an electron. It has exactly the same mass but the opposite charge. And when you put a positron and electron together, eventually they will annihilate and give out two gamma rays. And this is a mechanism that we actually use to detect cancer in bodies.
Right. It's
a lengthy story, but very, very useful, and a very important practical outcome of usage of antimatter. And positron emission is very common. Lots of isotopes of potassium. Every time you eat a banana, you'll get potassium isotope in your body that will emit positrons. It's quite healthy, wonderful thing, but nobody understands why there are so many electrons and so very few positrons.
Right.
Or more generally, why there is so much matter and so little antimatter. Now, it would have been very easy if we had no antimatter at all.
Yes.
We would never be even talking to each other about this, right? Nothing to explain. It wouldn't have been quite so challenging if we had equal amounts of antimatter and matter because of the symmetries involved. But having one by far overwhelming the other makes us ask the question, why this much and not that much?
Especially given what you were saying earlier on about symmetries.
Yes. So we have this problem called matter-antimatter asymmetry in the universe. So whoever sorts that out will win a Nobel Prize.
Right.
So there are people doing this, and we're part of that group. And the goal is to measure properties of antimatter to see if we can find that asymmetry. So at CERN, because they have, so it's the Large Hydron Collider is at CERN, and in Switzerland, and they can create antiprotons. So I talked about anti-electrons, but they can also create antiprotons. And when they create an antiproton, they want to combine it with an anti-electron or a positron to form an antihydrogen atom.
Right.
Why?
So
because
it's the same thing, but the charges are inverted.
Exactly. And why is that interesting? Because we know the properties of ordinary hydrogen atoms to 15 significant figures. That is the most accurate measurement
Yes.
you could hope to ever make.
Yes.
So, if you can make the same measurement on antihydrogen, there's a real potential for finding difference in those 15 figures, which will then identify some asymmetry between matter and antimatter. Well, Our job is to find a collision process that will help create and enough antihydrogen atoms so that those measurements can be done to that level of precision. So we're working with a group, and we had a number of high-profile papers on the subject in Physical Review Letters and Nature Communications, and the kind of calculations we're providing, we are the only people on the planet who can provide that kind of accurate information. But furthermore, and in fact they've made now, so about just over a year ago, there was a paper in Nature that said that they've measured this particular property in antihydrogen to the first 10 significant figures. And they happen to be the same as the first 10 significant figures for hydrogen. But there's still 5 more to go, and you have to make more antihydrogen. But that might sound a little bit sophisticated, but there's even a simpler issue. Because we don't have a good understanding of how to combine gravity with quantum mechanics, no one really knows how antimatter will behave under gravity.
Right.
Even that very simple question, if you drop an antihydrogen atom, what will happen? Nobody knows.
Go down or up?
Who knows?
Yeah.
Right? Now, there is not really a plausible theory that says it should be like anti-gravity. No. But you have to perform the experiment. And to perform the experiment, again, you have to make enough of this neutral so because gravity is so weak compared to electric charge and magnetic forces, so you have to have neutral antihydrogen. That's why you can't do it with positrons or with antiprotons separately. You have to bring them together to make a neutral atom to neutralize any forces associated with electromagnetism.
Yeah.
So the only force left is gravity. So you might want to just have a beam of slow-moving antihydrogen atoms and watch. Do they fall? Do they go up? Do they stay straight? Who knows? So again, there's two different Nobel Prizes there. One is for matter-antimatter asymmetry, and one is about attempting to unify gravity and quantum mechanics. Can we do this? So it's exciting from that side. So that's not so practical, if you like, although there would be very practical applications for anti-gravity, but of course we don't really expect, but you have to do the experiment.
Yeah.
So that's the more sort of traditionally, academically exciting aspects of the work that I do.
Yes.
Right? There's lighting, there's cancer treatment, there is understanding, what happens out in the universe, and there's those things where you really have unknowns. So that's why I really enjoy the work that I do. With the people I do. And that's one of the things, because that's the other thing I say to students. Choose a career by the people you want to spend your life with.
I like that.
Right? Because, workplace is sort of like not a forced marriage, but sort of like an arranged marriage. You choose the people, and sometimes you don't
choose
make
the
that
job,
choice.
but not necessarily the people around.
Yes. So I say, no, start with the people. See, these are the people you will spend your life with. And that's why my biggest job at university is to bring like-minded, high-performing students together so that they will form lifelong relationships, and they will choose careers to have a wonderful time, wonderful lives together.
Supporting and pushing each other.
Absolutely, yeah. So that's why I love my job.
What makes a good scientist?
Yeah, and it makes us.
No, it's a question. What makes a good scientist?
Oh, what makes a good scientist? Well, all those things that I've said. You have to have good people around you. So good people around you bring the best out in you. Right, and I am wired to love maths and physics, so the raw potential was there, but that raw potential is there in many people. And I think through biology and diversity, many of us have developed strengths in various areas that complement each other. It takes many of us to form a society. I love the expression, it takes a village to raise a child.
Yes.
Very true. right? And I'm part of that village. So I love the culture of science. So, for example, the culture of science is that it doesn't matter who the participant is. I have friends all over the world of different nationalities, of different cultures, but we are unified by our pursuit of science. And that's a wonderful thing. It breaks down barriers. In a similar way that sport and music do. Music is international, sport is international, and so is science. And these mechanisms are great for breaking down needless boundaries. Humanity has weaknesses in creating boundaries that are used to keep others away. This is unfortunate. And I think anything that breaks down those boundaries is a good thing. So what coming back to your question, what makes a good scientist? And that is strength across areas of A, being a good person, B, to have the intellectual strength to address the complicated world that we live in, but with a culture of inclusion, a culture of encouragement those who are better than you, very important, right? And that encouragement for others to be successful. So one of the challenges for me has been, as I've grown into a more senior role, is to enjoy success of my students and my colleagues ahead of doing things myself. That took a bit of adjustment.
Yes.
Right? Because
put your ego to one side.
Yes, yes. So, but that's okay now. I can do a little bit myself, much less than what I used to, but to provide that guidance and mentoring is something I really learned to enjoy. And so that's my job now. I'm more senior, I've been more successful, and people are looking for me to provide that mentorship. And it's a delight to see others succeed is very much part of my job. So perhaps there's a staged answer to your question. So a scientist who's junior needs to concentrate on their own things that much more. A scientist who's more senior has to broaden their outlook to ensure they are more inclusive of others around them. It's a more supportive role. Yeah. I don't know if that makes good enough sense.
No, I like that.
Yeah.
What would be one of the most exciting days of your career that you can recall?
The most exciting is, and I still remember the day, and as does my wife, because what happened was, so originally I took on this task and I saw there was an opportunity. So science is very opportunistic. I think I said that a bit earlier. And you have to find your niche, and you have to discover, when I took on the role and I changed fields and I understood what was missing, and I thought, well, I'm going to develop a theory whose validity is going to be independent of the projectile energy. Now that might not mean very much, but to those listening, but it was clear that there was a fundamental flaw in the way the field was at the time that I started. And I thought, well, here's an opportunity for me to make a mark for myself and develop a brand new computational theory that will do away with this particular weakness, that it would be valid at all energies, and hopefully it will explain the existing discrepancies between theory and experiment. So I had a goal. Nothing more important for a scientist than to have a goal.
Yep.
So I worked hard for 2 or 3 years. I developed the theory that I thought was it, right? And I applied it to the existing discrepancies between theory and experiment, and I got the same results as other theory that still disagreed with experiment. And I was distraught. After all that hard work, I made no progress, it would seem. Now, it turned out later that rather than giving up, I applied it to other areas so the most fundamental collision system would be an electron and atomic hydrogen. It's a three-body problem. We have two electrons and a proton. It is relatively simple. Could not get agreement with experiment for a simple excitation process. But then I thought, well, okay, well, what other information do I get from this? And another aspect of an electron collides with an atomic hydrogen is that if the initial electron has enough energy, it will ionize the atom. It will knock out the electron and create a free three-body situation of a free proton and two free electrons. Now, I knew this was theoretically a very difficult problem, unsolved, and it wasn't something that this was like leaping to the next stage.
Yes.
But I got access to 4 computers to run at the same time, different energy, and I plotted a very accurate experiment that had error bars of only about 3%. And after several hours, I would get 4 points coming up. And I had to span from the threshold, which is about 13.6 eV, to about 1000 eV. So it was going to take a lot of many hours for points to slightly come up on this. So I plotted all the experiment, but as every point came up, it was bang on top of experiment. And at one point, Anne still remembers, this is now 30 years ago,
yeah.
I said, Anne, come and have a look at this. And she ran, what? And I showed her that as my points came up, they were all going right on top of experiment. And that told me, I'm really discovered something here.
Yeah.
So having found, after many more hours, many days, and every point coming onto this curve, I actually suggested the original experiment that I was comparing with was wrong.
Right. And
it should be redone. And in fact, the ABC made a program for what it used to be called a Catalyst, and they called me the Electron Man. And you can go on YouTube and look at my name, and you can find this program. They made a discussion about this particular progress. How it's not too often that theorists will say experiment is wrong,
right.
But sure enough, roughly 5 or 6 years later, new experiments were performed. And they showed that indeed the theory was right all along. But in having developed this theory, it became the world-leading theory because I addressed the very original goal that I started with.
Right. Yeah. Superb.
Yeah. So that's the most exciting time. But there've been other exciting things, but that one's hard to beat because it's first.
Yes.
But other things, many other really wonderful things have happened since. So, having a theorist who's so confident of their calculations to the extent that when there is discrepancy with experiment, they will say, no, that experiment needs to be revisited. That doesn't happen often. So right. In my career, it's happened about 5 or 6 times now.
Right.
But on every occasion, we were able to show that the experiment was less accurate than what they thought. They had some... In fact, there was a paper published just last year. In fact, just today, I just realized another example is going to be published very shortly in the Physical Review A as a rapid communication, where we've made this prediction for a molecule. So a really exciting time, this time to be shared by my students.
Yes.
They're the ones who did the hard work of developing our theory for electron scattering on the hydrogen molecule, much more complicated than the hydrogen atom. And we found that our calculations were a factor of 2 smaller than the benchmark experiments that have been used for about the last 40 years as the correct results. We were a factor of 2 less. So we got in touch about a year ago with some experimentalists who developed a new technique for performing that kind of measurement, and they discovered complete agreement with our calculations. Just by coincidence, this morning I came in and it just says out there that the paper's been accepted for publication as a rapid communication in the Physical Review A. So it's very good timing.
Indeed. Superb.
Yeah.
What does the next 3 to 5 years hold for Igor?
Well, I'm I have been head of department for 7 years, and yet this year is a new beginning for us. So we have an incredible cohort of students. We have about 50 students whose median ATAR is about 95. It will completely change the dynamics of the department by the large number of outstanding students that we have. Furthermore, the reason we have these brilliant staff who are able to serve their needs is because we will be at Curtin building the world's largest radio telescope, the Square Kilometre Array.
Oh, up in...
near Geraldton,
yes.
within 3 hours of drive from Geraldton. Yeah, so that's phenomenal. So the opportunities for the students, the opportunities for the younger staff here are just phenomenal. It's just such an exciting time. I personally, it's not my area of strength. Radio astronomy is not where I'm at, but that's not my job anymore.
No.
My job is now to enable others to take advantage of these incredible opportunities that are here in our own backyard. So for me, there will be the aspects of my own field, which is very exciting in terms of this cancer therapy. So I'm right in the midst, and with my colleagues and graduate students, in supporting Australia's first proton therapy facility. That's going to be built in Adelaide. An interesting story, because that, you know how I mentioned that the protons can deliver their destructive energy just to the tumour and not to the healthy cells. That's based on a Nobel Prize given to the work that was done in Adelaide by a father and son team of William and Lawrence Bragg. 1915. They showed that with heavy particles, their destructive energy is delivered right towards the end of their travel. And now it's called the Bragg Peak.
Right.
And so, for very good reason, or somehow it is, I don't know, delightful coincidence, I don't know, that 100 years later, the advantage of taking the Bragg Peak to use it for cancer therapy will also be done in Adelaide.
Excellent.
Right, and it'll be called probably the Bragg Cancer Centre or something like that.
They'll have bragging rights.
Yeah. Yes.
It's a lame joke.
Yes, and so our research, my own personal research, and that of my colleagues and students, will thrive as it always has. But it is so much more exciting to be a part of a team that will enable outstanding research to be happening here in Western Australia. And this will change Perth forever. We will become like a university town, because the amount of industry to build this thing is phenomenal. It's huge. So it will be supported by fantastic industry, engineering. We need computer scientists, we need mathematicians, we need electrical and communication engineers. We have a double degree, I refer to it as the SKA degree, the Square Kilometre Array degree, because it combines electrical engineering with the mathematics, computer science and the physics. So the students who will, our top graduates from that degree, can choose. Do they want to go into building? Do they want to go into analysis? Do they want to go into in observation? Do they want to go into explaining? Or all combinations of those. So it's just a phenomenal delight to have the privilege of having that opportunity to really change WA for the better, and to really to put us on the world map in a big way. I mean, we already had a wonderful opportunity with the America's Cup, you know, that was in the 80s, but that's going to be quiet. We have a wonderful stadium now, fantastic. Hopefully our hospitals will be working well now that they've sorted some of these things out, and that's all great. But to complement that with the world-leading science, what an opportunity.
Superb. And something other than digging up molecules and exporting them.
Yeah, but to be truthful, even the mining industry is phenomenal in the technology that it has. In fact, something people don't realise, but the Western Australian School of Mines is ranked number 2 in the world. And here it is, it's at Curtin, based at Kalgoorlie. So number 1 School of Mines is the Colorado School of Mines, right, in the United States. But here we have number 2 in the world. And we don't promote it, but we should. Because again, they use the latest technologies. You know, people are talking about driverless cars. The mining industry has been way ahead for a long time in that space.
Indeed.
Right? So a lot to be learned from that area, from those technologies. So we have capacity to be successful on so many fronts. And we're just adding one more. Science, computing, mathematics, electrical engineering. Fantastic. Build the world's largest radio telescope. How brilliant is that?
It's very exciting.
Yeah, on top of all of this. And of course it will be done in conjunction with the engineers and the mining industries, because they will all get engaged. You have to have the resources to build this thing. You know? And you have to have the people to build this thing. You have to have manufacturing to build this. So this is why I love being a scientist. It is so constructive, so positive, and it's about taking everybody with you. Yeah.
Superb. Who has been the biggest sort of influence or mentor to you in your time?
Oh, the biggest influence
And what was the best piece of advice they gave you?
Well, the biggest influence in my life, of course, is my wife, Anne. You know, you can't. We spent 35 years together. We've raised 2 children together. A lot of difficulties you deal with together, and during her working life, Anne's salary was always twice mine, and so she is not only the kindest, most wonderful person on the planet, but she's one of the smartest people on the planet as well. So that is the biggest contributor by a long way. But my teachers, of course, the scientists who were lecturers, who have taken me under their wing, of course, are major contributors. My colleagues and even students to some degree, because if you have lots of different students, they all have their own difficulties, issues that they have to deal with, and you have to help them and adjust to their situations, and you learn a lot about yourself through dealing with difficulties that other people have. So, as I said, coming back to that wonderful expression, it takes a village to raise a child. It was a village that raised me. I lost my father at a much too young an age, so the last time I saw him, and I still see his face, is when I waved goodbye at the airport, leaving Leningrad at the age of 11. I never saw him alive again. My grandparents, my mother, family who sacrificed enormous amount. Not that they could have anticipated the tragedy that would unfold behind, but they did it for me, to get me out of what was the Soviet Union in 1972. And I have very conflicting feelings about that. I'm forever grateful because it's created an unbelievable life, and I'm forever guilty for the tragedy that unfolded in the background. I have to reconcile it. So my grandfather perished in Stalinist camps. He never saw my father being born, because he was denounced as a bad communist. It's horrific what happened in those times. I rationalize it that I have to be happy enough for my grandfather, for my father.
Right.
And I've done that job. And I've done that job.
Yeah.
My children are happy. My wife is happy. So, yeah. I'm an emotional person, of course, as you can tell. But it's what's made me as well.
Yeah. If you could go back to probably when you were about 12 and you're trying to make sense of Australia in English and all of that, if you could go back from where you are now and give that little boy a piece of advice in whatever language it was, what would you say?
Hang in there. You know, no, don't change anything. Deal with the obstacles in front of you as they arise. You have to learn the English. You have to go through this. You have to overcome the bullying that happens at school because you're the one kid who can't speak.
Different, yeah.
Right? It was interesting. It was interesting hierarchy I learned at high schools, at primary school. Now you had the Australian kids at the top who would beat up on the Greek and Italian kids. The Greek and Italian kids would beat up on the Yugoslavs. The Yugoslav would beat up on the one Russian kid. Very strange. You know, it was not something I saw. I imagine back in the Soviet system, we didn't have the diversity of nationality, but as kids in many places, if bullying was, some unsupervised kids will engage in, it's the Lord of the Flies scenario, right? And so I got to see it from the other side. I saw it as, I wasn't one engaging in it as a kid, but I did not know what it's like to be a victim of it. I had to deal with that. Now, it wasn't for very long, but it's left its mark. So it's made me stronger. Again, going back to what doesn't kill you is good for you.
Indeed.
Right? So in that sense, that's what I would say, and and I'd give the same advice to the younger people now. Don't shirk or go away from things that are difficult. Embrace the challenge, overcome it, because confidence, self-esteem, comes from overcoming adversity. People will say, I'm a very confident person. But, I've had a lot of adversity to overcome. And now I have confidence that I can overcome any more adversity that may come my way.
And face the unknown.
Face the unknown, yeah. Have the courage to face the unknown. To do things that are a bit different. So I guess whatever, I have no opportunity to go back and give that kind of advice to myself, but I have the opportunity to give that advice to the younger generations now, and I do. That's my job. Delightful part of my job.
Indeed.
Yeah.
Well, Igor, thank you so much for today. I've thoroughly enjoyed this conversation. It's been full of energy, full of emotion. It's been fascinating to understand physics a lot more. It's been fascinating to understand the world of physics around it, to research, and just to sit with you and your enthusiasm and your openness is it's quite something. I've really enjoyed it and really appreciate it.
Thank you for the opportunity. I really appreciated the conversation, and it's nice to be able to put science in perspective that is done by people.
Yes.
And every person has their own story. And it is a mistake to separate those stories from everything else, because it makes the whole.
Yes.
Right? And it's good that if we can communicate to the world that everything we do is social. Everything we do, anything that good is done in the world comes from people working cooperatively together. There was a lovely line, Stephen Hawking passed away recently, and apparently he had a wonderful quote that I really enjoyed. He said, "Everything that is good in life comes from people talking to each other. Everything that is terrible in life comes from people not talking to each other."
Yes.
Very, very wise sentiment, and certainly one that I share. And it's good to talk. Thank you for the opportunity.
Indeed. Igor, thank you for today.
Great pleasure. Thank you. Right.